Okay, so here's our 5-minute review that you can kind of, I'm just going to jog some memory things so that you can then go back, and if it doesn't make sense to you, rewatch some of those videos that talk about those concepts, because we do have that test tomorrow. So here you go. We started our whole circular motion thing by looking at the kinematic relationships, okay? So we paralleled everything. So we kind of did this whole big parallel between things that we already knew and things that became new, okay? So in other words, the things that we already knew in the kinematic sense is we understood that there is a d is equal to vi t plus 1/2 at squared, and vf was equal to vi plus at, and vf squared was equal to vi squared plus 2ad. Those were relationships that we very first began talking about. In fact, we did an example problem kind of to start to make sure that, yeah, these seem really easy now. So then how did that change when we went into the new stuff? Well, the new stuff, we said, okay, d now becomes theta. So we're now looking at displacement in an angular sense. So how much angle did we change instead of how much displacement did we change? And our v now became omegas, and omega just mean that we have an angular speed or an angular velocity, and our a's then became alphas, and that was our angular, okay, acceleration. So now again, for those of you, a lot of you call this one W, some people call this one the fish one, but remember, this is angular acceleration, angular velocity, and angular displacement. So then we had some relationships that we looked at, okay? So again, under the average sense, we always said that a velocity average was equal to a displacement divided by time. Well, an omega average was just our displacement divided by time. So again, we had that kind of a relationship. We do equate distances in an angular sense to an arc length, and so we did look at that in terms of an angle can be related to this arc length over some radius. So again, further you get away from the radius, the bigger the arc length that you take for that angle. And that was a big relationship thing for us when we started to talk about other things. Let's see, so again, all of these then transferred into theta equals omega I t plus 1/2 alpha t squared, and omega f equals omega I plus alpha t, and omega f squared equals omega I squared plus 2a theta. Okay, so again, these are the relationships that we looked at kinematically. Okay. When we did get to the point when we started to look at kinematics and we said, okay, this is the good relationships here, what did we do next? Well, the next thing that we did was we started to talk about Newton's laws. Okay, so Newton's laws then said, well, we have the first law, which was the law of inertia. We had the second law, which was F equals ma, and we had the third law, which was for every action there's our action-reaction pair law. We started to then take this to this type of a level. We looked at velocity. Okay, hold on. Velocity is a vector. Okay, and so since it was a vector, if we're traveling this direction around some circular path, as we change our angle, we change, okay, direction. Changing direction equated into an actual acceleration. So why did we get this acceleration change? Because we changed our angle. And what do we call that? Well, we called that our centripetal acceleration. So centripetal acceleration was an acceleration due to the changing direction. Okay, so we had centripetal acceleration, changing direction, acceleration. And then we had tangential acceleration, which was changing magnitude. So we had two different ways to look at now acceleration as we started to transfer into this kind of curve stuff. And that brought us into our force concept, which said that we then have this net force, and I always call it a net force, but the net force became that centripetal force. And the centripetal force was nothing more than a mass times a centripetal acceleration, just like when we talked about net force was equal to a mass times an acceleration. So it's the same type of a situation. We had to start drawing free body diagrams again. Oh, I'm probably writing over my picture. Free body diagrams again. Okay, and so we had to draw pictures and know that Fg went down and Fn went up, and maybe we had a force that was our friction force there, and that's what caused us to go in a circle. So we had a number of different ways that we started to equate that out, and a lot of different problems that dealt with that. Okay, oh, back to a different slide here. So we had some ways that we looked at centripetal accelerations, okay, from a mathematics sense. We could do it with tangential velocities, okay, or we could do it with an angular velocities. Okay, so again, relates back to the radius in that angular sense. Let's see, we had other ways that we could figure out tangentials. Tangential speeds were always in relation to the angular speed and the radius, and our tangential acceleration was related back to the radius and the angular speed. So again, we had relationships that built those things up. Okay. Now, at some point we started to say, okay, this is our parallels. We started to look at forces. How does this relate to other things? Okay, and what did Newton do with all of this stuff? Well, Newton said, okay, first of all, we have first law, which says that an object at rest tends to stay at rest, an object in motion tends to stay in motion. So we started to say, well, objects that are in rotation want to stay in rotation. Objects that are not rotating don't want to rotate. So again, it's that same law of inertia, which brings us up to this concept of a moment of inertia. Okay, and a moment of inertia was that whole thing that we just saw, most recent video, where as a tire is turning, it wants to continue to turn. It deals with the mass of the object, it deals with the shape of the object, it deals with the makeup of the object. So again, it's a momentum type of, or I should say an inertia type of property. In our generic sense, we said that it's like what we would do in calculus, where we sum up all of those parts. So our moment of inertia becomes the sum of the mass particles with their radius, or the distance that they are from the rotation squared. Okay. Now this gets us into looking at a lot of different situations. We can look at things in terms of Newton's second law. Second law says that F equals ma. There's a parallel to this, and that's our torque is equal to moment of inertia times angular acceleration. So again, this is our parallels between the two, and that net torque is what's provided. Now, how do you get torque? How do we provide torque? Well, torque comes about by having a force, okay? There has to be a force applied at a distance away from some rotation point, okay? And so we looked at that from the sense of torque is nothing more than a force applied from a distance. And we had the wrench problem, okay? So in other words, if I'm pushing on this wrench, I provide rotation, okay? Now the rotation, or the arm that we're looking at versus the force that we're applying, has to be perpendicular to each other, so remember that. We use this relationship then to look at an equilibrium stance. So if the object is at rest, it's going to be at rest following the forces, okay, as well as the rotations. So we built a bridge and we looked at beams and things like that. Then we get into looking at our other concepts. So concepts of energy, concepts of momentum. And both of these have rotational components. So when we look at energy, energy is nothing more than can be transferred into a rotational sense. So we can have rotational kinetic energy. And that kinetic energy in a rotational sense was 1/2 I omega squared, which did come out to be in joules. So that's what our typical energy was. We can now add all those energies together. And we also had a momentum, which we said was now the I omega. So again, it's back to the relationships between the things that we had before. Momentum was our skaters. Okay, skaters get on there, they start to change their shape, change their moment of inertia, okay, and that changes their angular speed. Okay, so it's a conservation type thing. We look at how much momentum we have and how much can we get. Okay, conservation of momentum. We looked at the energy that's associated with it. So if I'm rotating about some point, I have some kinetic energy that's involved. So again, if I have a ball now rolling down a hill instead of just a block sliding down a hill, there's rotational kinetic energy involved as well. Okay. So really that's what we're kind of doing. It's our everything in a nutshell, and I think I've got it under 12 minutes. I thought it was going to be under 5. My suggestion is if some of these concepts are kind of still not 100% good in your mind, go back and rewatch the video, and then make sure you do the readings that go along with those. Okay? And good luck on the test tomorrow. As a side note, I will be gone tomorrow, so that's the other thing, is that you'll have a sub here while you're taking your test, and hopefully everything goes well for you. And like I said, I'll see you then on Friday.